Okay, could you see my slide? Yeah, okay.
And we can hear you.
Okay, so I'm Shingo Hirano from Japan. And okay, so today I will talk about my recent work about the supermassive formation on the diaphragmatic gas cloud. So this is a problem of the high mass end of the Popsi IMF, as shown in Tillman talk. So today I show my new simulation of the my magnetic hydrodynamic simulation result of the supermassive formation in magnetized atomic cooling gas cloud, and how the and show the effect of the magnetic field on the supermassive formation. Okay. So this slide, in this slide, I would like to show the motivation of this study. So the goal of this study is to show the formation channel of the seed black hole of the high-Z quasar or supermassive black hole, which observed at redshift 6 or more. And such a very, very massive object with about 10 to 9 solar masses is observed, but the origin is unclear. And to form such a very massive object, we should explain the formation of the very massive object about 10 to 5 solar mass as the first formation era, which is called as an intermediate mass black hole, or IMBH. And one possible channel of such a one possible formation channel of such a supermassive object is the diaphragmatic black hole scenario, and which is about the rapid collapse of the chemically pristine, so zero metallicity gas cloud with 10 to 5 solar mass, and which forms about the same mass supermassive star and same mass black hole. Okay. So, previously, many researchers studies such a formation channel. And to form such a very massive black hole, researchers consider the atomic cooling halo because inside such a halo, the very high accretion rate and the constraints of the fragmentation are realized. And until now, many formation channel are considered as listed here. Sorry. Okay, so as listed here. So, and theorists should answer the sum of the formation rate of the SMB sheet and compare such a formation rate with the observational rate of the high-Z quasar. So this is the current condition of this topic. But there is one unexplored factor of this study. It is the magnetic effect, and this is the main actor in this talk. So because the magnetic field in the universe are considered to weak, so emission effects are usually neglected in the previous study or the many simulations. However, in some study and also recent studies says during the star formation during the first star formation, some amplification process can enhance such a tiny B field to the very significant value, and such a strong magnetic field can affect the accretion history, fragmentation, and final stellar mass of the first star and first supermassive star. And in the supermassive first star formation cases, recently Greater et al. Shows the simulation of the magnetized atomic cooling halos, and they show the amplification process of such a primordial very tiny B field, but B field. However, they stop simulations at the end of the collapse phase. So at the era of the formation of the stellar core, and they didn't study the magnetic effect during the accretion phase. So in this study, I'd like to check the effect of the influence of magnetic effect during the early accretion phase by performing the MHD simulations. Okay, so in this slide, I summarize my simulation setting in this slide. I use MHD simulation, non-ideal MHD simulation code I used in my previous studies, and the important point is I changed two parameters of in this study. One is the initial magnetic field strength from the zero, non-magnetic cases, and from 10 to minus 12 Gauss. This is the typical value in the at the first formation error. And 10 to minus 5 Gauss. This is very, very strong cases, and similar with the predicted star formation. And as a second parameter, I change is metallicity. The one case is the solistic case, so zero metallicity case, and one is a bit a metal-enriched case, so with 10 to minus 4 solar metallicity. It is because in recent study by John and Omkai, they show the formation channel of the supermassive first star in such a metal-enriched case. So I also checked the magnetic effect on such a case. Okay, and in the following slide, I will mainly show the physical cases with initial B field with 10 to minus 12 Gauss and the general metallicity case. So I will call this as a physical model. Okay, so let's go to the physical result. So in this slide, I show the result of the physical model and the first evolution of the first 300 years after the first dense core formation. So, or in other words, the first star formation. And in the below three panels, I show the to the density map and B field strength and the proton beta value, which is the ratio of the thermal pressure and the magnetic pressure. So this shows the importance of the magnetic pressure, the magnetic effect compared with the thermal effect. So let's go. So let's start the movie. Okay. So just after. So okay. So. Okay, so and this is just after the first formation cases, and after the first formation, the second and third fragments forms, and nearby such a small tiny fragment, the B field, the magnetic field are strongly amplified, because such a small tiny field, because the moving and rotation of such a small tiny core can efficiently amplify such a B field. And as a result, the proton beta value declines strongly, and it means the B field effect becomes important. And as a formation of the multiple fragment, the B field, the strong B field region expand. So this is the basic result of my simulation. Okay, so let's let's summarize the result as this slide. So this figure shows the radial profile of the density and B field. So at the time 0, or just after the first protostar formation, the B field strength becomes 10 to 6 Gauss as a center of the protostar. However, just after 10 years, the B field quickly amplifies to 10 to minus 2 Gauss. This is due to the rotation around the first core, the first dense core. And after the 100 year and 500 year, such an amplified region expand due to the formation of the later dense core and its rotation. So this is so this means during the accretion phase or during the very early accretion phase, the B field strength can amplified around the surface regions. Okay, and this slide shows the evolution of fragment the fragment properties. So number and mass of fragment. So because of the very efficient merger, the merger rate, the fragment number is not so different. Not so different. However, the most of the fragment can merge to the primary one. So the most of the fragment mass is held by the primary core or central one. So this small figure shows the mass spectrum, and you can find the primary core have the most of the mass. Okay. Okay, and this slide shows the comparison of the magnetic case and non-magnetic cases, and I find by adding the magnetic effect, the mass growth of the total mass of fragment and the primary fragment differ greatly. Okay, so in the last slide, I will show you the dependence of the two parameters. One is the initial B field strength, and I find so this figure, so this line color shows a different initial B field strength, and the yellow color shows a very strong initial B field, and blue color shows the tiny B field. So in the case with a very strong B field, about 10 to 5 or 10 to minus 6 gas cases, in these cases, the very early supermassive formation can occur due to the strong angular transfer and the merger rate, I find. But in other cases, the growth, the amplification, and the time growth is very similar. And finally, I show the effect in the case of the metal-enriched cases. And in such in metal-enriched gas clouds, because of the low temperature of this cloud, the mass accretion rate decrease. However, in the case with the very very high initial B field cases, it can occur in the metal-enriched cloud, which experience the faster formation. The very massive supermassive star formation can occur. So this is this shows this just supports the formation of the supermassive fast star in the metal-enriched cases. This is the final result of this talk. This is the summary slides, and I end my talk with this slide. Thank you.
Thank you so much, Shingo. Those are amazing simulations. Thanks so much. Simon is asking, how do you enforce the divergence of the B field is equal to 0 constraints in these simulations? What's your method?
Okay, I find your question in Slack.
Yes, diff B equals 0.
Ah, okay. Okay, I check it in and
like, how do you force that this is happening in your simulations?
I'm sorry. Sorry, Simon. I can answer it after my talk in Slack.
Yeah, it sounds like a very technical. That sounds great. John also has a question, and he wants to know if you tested to see if the small scale dynamo is enhanced, if the gene's length is better resolved. referring to Federat and Turk, who went up to 128 cells per gene's length. So I think this is also a resolution question.
Yeah, it is important questions, and in this simulation, I didn't change the resolution during the collapse phase, and in collapse phase. So as your questions, if I enhance the resolution, the initial amplification factor can be enhanced. However, I think such a difference can be tested by in my simulation by changing the initial B field strength, because this difference can give the same result with resolving the high resolution cases, I think.